Well, we finished chapter 4 and learned about probability and different forms of probability. And now we're attaching that concept of probability to the bell curve and the knowledge that probability is between inclusive, excuse me, is inclusively 0 to 1, with 1 being a certainty. Well, now we're going to have the concept of area under the curve to equal 1 or 100%, and therefore can predict probability. By that measure. We'll take some byroads before we get to this end result. And the one we're going to take first is discussing the random variable. I have runny nose. Excuse me. The random variable is typically represented by x. So it is an x representing each data value that has a single numerical value. That means it is 0 through 9. Determined by chance for each outcome of a procedure. A probability distribution, well, actually, it could be any number. 0, let's just say 0. It's not, it's any number. Okay, I feel better about that. The probability distribution is a description that gives the probability for each value of the random variable and is often expressed in the format of a table and formula. So what we're talking about first is that all probability is 1, and we're going to use that factor for each distinctive variable x, and x is a counting number, so that's going to be important. So we have more definitions, and these are from the textbook. A discrete random variable has a collection of values that is finite or countable. And what this does is tell us, like the tossing of a coin is heads or tails, and we can do not measurements, but chances of something occurring, knowing the sample space and how many variables x, random variables, we have. Continuous random variables have infinite values, and the collection of the values are not countable. So that's what we have. We studied that in chapter 1 about discrete and infinite, continuous. So we also are learning something new, the notation of 0 with a plus after it. This means the probability so unlikely it resembles 0, but is not 0. So 0 plus is something you might run across to with. So let's talk first about the requirements for a probability distribution. Now remember, probability is the P of X, and we've known that. And the probability is of an event. Well, here, the X is the assigned value or values that you have to arrive with. And each variable, each random variable, has a probability. All right, so let's look at what we have as a requirement. There is a numerical, not categorical, random variable X, and the values are corresponding probabilities. The sum of the probabilities of the random variable X equal 1 to be a probability distribution. It may be close to 1 as well because of the rounding issues. Probability is between 0 and 1 inclusive for every individual value of the random variable X. So then we come into parameters, and those are extents. Now, when we talk about parameters, we're talking about population. So in these probabilities, we're talking about all considerations under whatever we're studying. And so that's why we're using parameters. And that means that we'll have things like mu, which is the mean for a population. We'll have theta, which is the standard deviation for a population. We'll have a theta squared or variance of a population. And then we'll have also the X, the P of X, which is the probability for a specific random variable. Our examples will make sense of this. This is an easy section. We struggled through probability, so we can get to this and use the information to acquire probabilities of, uh, of distribution. So we have mu is the sum of the variable X times the P of X, which is probability. So that means a sum. So we're taking the sum of each X variable times the probability of it occurring. The standard deviation has a kind of complex formula. And what we're going to use is this guy right here, which is standard deviation, the square root of the sum of the random variable squared times the probability, the sum of all of them, and then minus the mu squared. So let's do some examples. All right, here we go. Understanding the material. That's the first one. And we always try, I always try to make sure that we have examples that can give you a handle on the vocabulary. For 100 births, the P, exactly 58 girls, is 223 10,000ths. And the probability of 58 or more girls is 67 thousandths. Is 58 girls in 100 births significantly high number of girls? Which probability is relevant to answering that question? Consider a number. Consider a number of the girls to be significantly high if the approximate probability is 5% or less. All right then. So as we outlined what we are told, we want the probability, we know the probability of exactly 58 girls born is that value. The probability of 58 or more girls born is small. The quantity of births of this sample are 100 births. Is 58 significant? So it is not significant. All right, so we can say that the first one, the probability of exactly 58 girls born out of 100 is 2.23%, and we do know that the 2.23% seems to be less than the 5%, but we have to take one or the other. So the 58 or more, this is significant. It's small, okay, but they want significantly high. And so that one is small, so that doesn't apply. So then we have the other one, which is this one, which is the probability of 58 or more girls is, this is that number, which gives us 6 7/10%. And we know that 6 7/10% is greater than the 5%. So that one is significantly high. I have a tickle in my throat, and it is upsetting me. Let me see if I have a lozenge. Oh, no. That is because the relevant probability greater than 0.05. So the one that says 58 or more girls is more significant than the one that's exactly that amount. Let's look at another example. And this one exposes us to the value of learning what a probability distribution is. So here we have 5 males. Notice we have 0 through 5 males with X-linked genetic disorders have 1 child each. Okay. X is the number of children among the 5 who inherit the X-linked genetic disorder. Whether a probability distribution is given, find its mean and standard deviation. If a if a probability distribution is not given, identify the requirements that are not satisfied. All right. So the first thing we need to do is satisfy that does a table show a probability distribution? That means that the sum of x must equal 1 to prove it is a probability distribution. Okay, so we're going to add them. My calculator. I'm going to clear everything. Make sure you can see it. And I'm going to add the P of X. Decimal 034 plus decimal 161 plus sorry about that, decimal 305 plus decimal 305 plus decimal 161 plus decimal 034 and hit a total. And I get 1. So I can safely say, yes, the table shows probability distribution. Sum of the P of X is 1. Okay, so that's our first step. Find the mean of the random variable X. Now we know that the formula for mu, which is the mean, is the sum of X times P of X. So we're going to use this up here. Say 0 times P of X is 0. 1 times 161, and decimal 161 is decimal 161. 2 times 305 is 610. Sorry about that. So I'm looking at all those values, and 3 times a 305 is 915. And 4 times, I'm going to have to do the calculator on that one. 4 times the 161, decimal 161, is 644. And 5 times the decimal 034 is 17. Decimal 17. All right, so we're going to add them. And so I will. And on the home screen, I'm going to do the decimal 161 plus the decimal 610 plus the decimal 915 plus the decimal 644 plus the decimal 170. And I get 2 and 5/10. So mu equals 2 and 5/10, according to the formula that we needed. And now we need the variance, or actually the standard deviation. The formula that we said we would use is that theta equals the square root of the sum of x squared times p of x. And once we get that, we're going to subtract mu squared. All right. So let's make a little table here. Have our x is 0, 1, 2, 3, 4, and 5. And then we have our p of x as decimal 034, decimal 161, decimal 305, decimal 305. You can tell it's almost a bell curve too. Decimal 161, decimal 034. And our formula says that we want x squared times p of x. So this one's 0, because 0 squared is 0. So then 1 squared is 1 times the decimal 161. 2 squared times, on the next number, is 305. 3 squared times, again, 305. 4 squared times, that looks weird. Well, all my numbers look weird. 4 squared times the 161. 5 squared times the 0.034. So we're going to get this and then get the sum. I have 0, decimal, 161. So I'm going to get my calculator so you can follow along with me. Little math. And this one's going to be 2 squared times decimal 305, sorry about that. And I get 122. And then I have 3 squared times decimal 305. 2 decimals, 745. 4 squared times the decimal 161. 5 squared times the decimal 034. Got the 0. 85. And I'm going to add this column up. So here I go. I'm going to do decimal 161 plus 1 decimal 22 plus 2 decimal 745. Oops, sorry. 45 plus 2 decimal 576 plus decimal 85. Okay, let me double check. 161, 1.22, 2.475, 2.57. Oops, should be a 6, and 80.85. And I get 7552. All right, now let's put this together now. Remember that the standard deviation is going to equal the square root of the sum of x squared times p of x minus mu squared. All right, well, we just got this part right here. Square root of the 7.552, and of course the mu is 2.5 squared. So we're going to do that on our calculator. Second square root, 7.552 minus 2.5 squared, and hit enter. And I get this number, 1.141105, and so on. They're going to ask you to round to the first one decimal because it's an approximation on probability. And this is our standard deviation for the population. All right, so we've answered all of the questions for this particular problem. Using first the check to see that it's equal to 1. Then finding mu, which is the independent variable x times the probability, and the summation of all of them. Then we did the standard deviation, which I used the x squared times the p of x, the summation of all of them, minus mu squared. And I came up with one standard deviation of 1.1. Okay. So here is another one that we want to look at. Ted is not particularly creative. He uses the pickup line, and I forgot the K, and there's a couple of spellings here, I'm sorry. If I could rearrange the alphabet, I'd put U and I together. Silly. The random variable x is the number of women Ted approached by encountering one who reacts positively. Determine whether the probability distribution is given. If a probability distribution is given, find the mean and standard deviation. So our first step is to add the p of x. All right. Well, these look very small, as you can tell. So let's add them up anyway. 0.001, 0.008, 0.027, 0.064. So let's see what kind of total I have. Got the O, didn't it? Not the O, 0. And I got 0.1. Well, that does not equal 1. So we can't do any other of the material. It can't happen unless this equals 1. Well, it does not equal 1, so the whole thing collapses. All right. Okay, so now we're making sense of the results, significant values. Now remember, we're always measuring data to the structure. of the probability distribution to gauge significance. And we've used it in chapters 3, 4, and 5. And we've had the same information each time. And that's the range rule of thumb of identifying significant values. A significantly low value is mu minus 2 thetas, or lower. Significantly high are mu plus 2 thetas, or higher. Values not significant are anything between the low and the high. So here, we have an accompanying table. Describes a random variable x, the number of adults in groups of 5 who reported sleepwalking. So we've got 1 through 5, 0, 1 through 5. And we're talking about the probability. So we want to first add them up. So we need to see it adds up to 1. So here we go. We're going to take our calculator. Nothing difficult. It always saves you work and aggravation if you do the steps. So I'm going to enter the 181 decimal. 370, 302, decimal 119, decimal 023, decimal 005. I get 1. It does. So we can continue. Okay. Well, the next thing we want is the structure of the probability they want us to look at. Okay. So they're asking us, now let's read it again. First one is find the probability of exactly 4 sleepwalkers. Well, all we have to do is look at the table. For x equals 4 and see p of x value. All right, we're going to do that. So if I do 4, I've got that value right there. It's about 2%. Now let's read the other one. Find the probability of getting 4 or more. So that means that we, again, look at the table and add x equals 4 and 5, p of x's. All right. So we're looking at the table. So of x equals 4 is 0 to 3 plus p of x equals 5, which is the extent, plus 0.005. So we get 0.28 is the probability of getting 4 or more sleepwalkers in this study. Nothing hard. Well, then it asks us to make an inference. So here we go. Which probability is relevant for determining whether 4 is a significantly high number of sleepwalkers among 5 adults? The results are parts of A through D. Specifically said 4, whether 4 is a significantly high. So the P of x equals 4 is 0.023. So we're going to evaluate 0.023 with 0.05. Well, this guy is less than that guy, isn't it? And between A and B. And okay, so it's less than. Now, the other one is 0.028 with 0.05, and that is also less than. Since the probability of getting 5 sleepwalkers is less likely than getting 4 sleepwalkers, the result of part A is the relevant probability. Part A was this guy right there, the lower. That's not right. Since the probability of getting 4 sleepwalkers is a result of part A, this is, no, it's not irrelevant. Because they're talking about, now remember what they're asking, significantly high. Since the probability of getting 4 or more sleepwalkers is a probability of the given or more extreme result, the result from part B is relevant probability. And that's because it encompasses more. And that is the answer. Since the probability of getting fewer than 4 is the complement, no, that doesn't even make sense. It's not there. Now we're using the 0.05 for the threshold of the 5 adults. And we talked about the fact that these values are significantly less than 5. And therefore, it is a significantly high number because it's less than 5. All right. We're going on expected value. Expected value is calculating the expected value of understanding the mean, the mu, where, let me get this on, a random variable x is utilized to compute the 2 types of probability, probability of win and probability of not win. And these are concepts of how we figure out what we're going to either make in money or lose in money. And these are called expected values. And it involves the amount of money you put in to purchase a chance of winning. It says find the total number of sample space is number 1. Calculate the probability of winning in ratio form. Compute the P not winning in ratio form. Now consider the cost of participation in lotto as expense. That means an outright investment of the money. Now chart the variable x in the form of investment amount times the P of x for winning and losing and add to arrive at mu. Here's our example. All right. it'll make sense once we get to the example. In a state lottery, you bet $2 by selecting 3 digits. So cost to gamble is $2. Now you're already in the hole, $2 into this for 3 digits from 0 to 9 inclusive. So the cardinality of the set that we're making the numbers from is 0 to 9. So our sample space of digits alone is the set 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if we did the cardinality of our sample space, we'd have 10 digits. Okay, the thing is we can do 10 digits on the first number, 10 to select from, 10 digits from the second one, and 10 from the third. So how many different ways can selections be made? Well, there's 10 digits on the first, times 10 digits for the second number, times 10 digits for the third. 1,000 ways. Select 3 numbers. All right. So now they said, what is the probability of winning? Okay. The probability of winning one specific number and in our sample space is that 1,000. So it's going to be 1 out of 1,000. All right. So now that's our probability of winning this particular 3-number lotto. Okay. So now we want expected value. Okay. Now we're assuming that we're going to win. So our expected value is $400 because there's $400 you can win and collect $400 minus the $2 that you spent. So our expected value of winning is $398. Okay. Now this one's interesting and a little bit on the rough side of how we perceive what we can consider in the betting genre. If you bet $2 on a certain casino, so this is our cost to participate. So we're getting a negative $2 in a certain casino game. The expected value is a negative 35 cents. Well, actually 3.5 cents. Sorry about that. Which bet is better in the sense of producing a higher expected value? A $2 bet on a state lotto or a $2 bet on a casino? Okay. Now remember, we did the lotto, the 3-number, and they want us to figure out what we'll make, right? So we had the negative $2 plus the $400 times 1 over 1,000, and we have a net of $1.60, negative $1.60. So on the next one, we have the 0.35 on the casino. Well, the casino is a better deal. Even if we lose, we get $1.60 as we work through all of what we can do. All right. Well, we're done. Have fun doing this homework. And we know that the casino game is a better bet because it is a larger expected value. In other words, we just lose 3 cents versus losing $1.60 on every trial on the other one. Thank you for listening. Do the homework.